Hi, this is Si-Ioi from the Department of Electronic Engineering at Chinese University of Hong Kong. This study investigates the use of consonant-vowel segments in the detection of disordered speech. We focus on children with speech sound disorder. The disordered children encounter persistent difficulties in producing specific speech sounds, and it is very common that they substitute the desired phoneme by other phoneme. This table shows some examples of the substitution error made by the disordered children. The distinctive symptoms of speech sound disorder can impact the education and social life of the children. Given the shortage of therapists in the group, systems that carry out automated detection is highly desirable for the effective treatment and rehabilitation of the disordered children. In our previous studies, we performed the detection using only the consonant segments, which are the segments highlighted in yellow as shown in this figure. But we encountered challenges in the detection on unaspirated stop consonants, and we suggest the reason is that the production of these consonants involve a long duration of closure that subsequently makes the speech segment easily interfered by the background noise and makes the detection more difficult. It is known that the acoustics of the vowels can be affected by the preceding consonants, as shown in this example below. We have the same Cantonese syllables pronounced by a healthy speaker on the left and a disordered speaker on the right. By inspecting the spectrogram, we observe that there is different phoneme transition in the vowel segments. And the reason is that the disordered speaker makes a substitution error in the consonant segments. In other words, the co-articulated vowel segments may exhibit atypical acoustic features as the disorder occurs. This observation motivates us to incorporate such consonant vowel segments in the detection of disordered speech. This is the detection system. It aims to decide if a consonant error occurs in the test segment. The system first receives the test segment and the reference segments, and these segments pass through the embedding extractor, which is a neural network, and the embeddings are derived. After that, these embeddings are compared in the pairwise manner, and a decision threshold is applied to the similarity scores to make the final decision. Here, the reference segments are selected from the healthy speakers, and one or multiple reference segments can be selected during this pairwise comparison. Regarding the details of the computation of similarity scores, for each pair of segments, that means a pair of test segments and a reference segments, we compute the cosine similarity and the binary similarity. After that, we can linearly combine the binary and cosine similarity scores for each consonant or consonant-vowel test segments. Furthermore, we may also fuse the score calculated from the consonant and consonant-vowel segments of the test speech and derive the final score for the detection. This study is focused on Cantonese, a major Chinese dialect spoken by over 70 million of people in the world. In this language, we have 19 consonants, and particularly we are focusing on the substitution error on the initial consonants of Cantonese. To train the embedding extractor, here we deploy two datasets. The first one is called Si-Ioi. It supports the system development for the speech sound disorder detection. All the child speakers in the Si-Ioi were assessed by the standardized articulation test, and the speech material includes 130 Cantonese target words selected by the database. The second dataset used in the training is called Si-Ioi. It is an adult red speech corpus and used to increase the data size for the neural network training. The number of segments used in the training are shown in this table, and all these segments are obtained using the forced alignment by a speech recognizer trained on these two data sets. And the segments can be grouped into 19 consonants or 173 consonant-vowel units as the training targets of the neural network. Regarding the structure of the embedding extractor, we use a 3-layer bidirectional gated recurrent unit with 400 hidden units in each layer. And for the input, we are using 80-dimensional filter bank features with linear variance normalized, and the embedding extractor are trained based on the recognition task, recognizing the consonant units or the consonant vowel units using the objective functions of cross entropies. And to evaluate the detection performance using the embeddings, we are using the equal error rate and area under curve as the evaluation metrics. Here is the experiment results. In the first task, we evaluate the detection systems on distinguishing between the typical and disordered speech sound. And from the table, we can see the improvement can be achieved by either adding adult data in the training of embedding extractor or fusing the similarity scores of consonant and consonant vowel segments. From the rate that achieves the best ER and AUC, we can see that both the similarity scores from the consonant segments and the consonant vowel segments are contributing equally to the detection process. At the first glance of the table, it seems that without the fusion, using consonant segments only always performs better than the consonant vowel segments. To verify whether the consonant vowels is effective, we divide the test data into different groups according to the consonant IDs, the consonant identities. So we further divide the test data into 12 groups that represent 12 types of consonants. And we redo the detection task and see their performance. And from this table, we can see that actually using the consonant vowel embeddings improves detection not only on the unaspirated stop consonant K, but also in some other types of consonant. So they are highlighted in blue color. And on the detection of each type of consonant, combining the similarity scores from the consonant and consonant vowel segments still deliver the optimal performance in most of the cases. So to summarize these studies, we find that jointly using the consonant and consonant vowel segments can deliver optimal performance in the detection of disordered speech. And we once confirmed that using the consonant vowel segments is effective to solve the challenges we encountered in the previous studies. And also for this type of application oriented to child speech, mixing the adult speech in the training of models is effective to improve the performance. In the future, we are interested to carry out in-depth analysis of the consonant-vowel interaction in the child speech, and also carry the segment-level detection to a subject-level detection of the speech sound disorder in child speakers. And that's the end of this presentation, and here's the reference. Thank you very much.